recording here. Alrighty. So I'm going way back in the slides right now. I'm going back to, I think this is slide 7 or so, just to retouch on this because it'll make more sense to where we left off in class the last time. But if you recall back when we were discussing reversible and irreversible processes, we were discussing, these, when we have basically more or less a constant temperature T, that when we see this entropy change, right, the entropy change from the system is that, onto the surroundings was, can be reversible, because if it's incrementally small, if we have that change going in the opposite direction from the surroundings onto the system, right, with this infinitesimally small change in temperature that exists. And then we discussed the irreversible process, but we went on to discuss entropy a little bit further and had come up with this equation here that the change in entropy is equal to the heat in the reverse direction, right, divided by the temperature. And we talked about, the heats of fusions and how we could basically substitute heat from heat of fusion times the number of moles. And so we're basically talking about a process where, it makes sense. You have an increase in entropy if you're at a constant temperature, right? So if we're talking about at a more or less constant temperature, the amount of disorder is directly related to the reverse of the heat, right? So if you start increasing the heat of a process, right, and your reverse of that heat, right? So if your entropy is increasing because your heat is increasing, let's say you have a vessel, right? You warm and you're able to increase the enthalpy of that. So you're going to expect these particles to start moving faster, right? The kinetic energy is increasing of these particles. If you would expect entropy to also increase because these are moving around more quickly. But in the reverse direction, that heat would be, the heat in the reverse direction you'd expect to be going in the opposite direction, decreasing, right? So that's what we're talking about here, is that entropy is equal to the reverse of the heat of that process of what's going on. And now let's jump ahead forward to where we were. Slide 31. And it's switching. All right. So where we left off was, well, my computer's going really slow right now. I don't know what's going on. I'm pushing buttons and nothing is happening. Nothing really using all my memory up. Let's see. Oh well. Continue onward. Hopefully this will continue to work. All right, so heat, when we talk about entropy changes in the surroundings, right, heat that flows into out of the system changes the entropy of the surroundings, right? If you can imagine, if you have an isothermal process, which is what we were talking about back in that picture originally, where you have a constant how isn't this working? Sorry, everyone, my I'm not able to do any writing or anything right now. My computer's completely frozen. Technical difficulties. Let's see what happens here. Oops. Just trying to restart PowerPoint. See if that's my problem. Sorry everyone. I'm just trying to restart my computer here. I mean, restart and close programs and seeing if I can solve this problem. All right. All right. Let's see if this works now. All right. There we go. Back up and running. So let's go back to here. So if we were talking about an isothermal process, just like we were talking about in that picture where you have more or less infinitesimally small changes in temperature, we discussed that, you know, our entropy, right, the entropy of the system, right, is going to be equal, I mean, when we were discussing it back then, right, we were talking about delta S of the system is equal to the Q of the reverse over T. Right? And if you think about what this means here, right, if the Q reverse in this case, right, is going to be the heat of the surroundings, right, because the heat of the surroundings is going to be the reverse, which is the heat of the reverse of the system, I should say. So if we look at this, when we're looking at the surroundings, now we're looking at the, heat, the heat of the surroundings is going to be equal to the heat, the entropy of the surroundings, the change in entropy of the surroundings is going to be equal to the heat of the surroundings over T, which is minus the heat of the system. So you can see the relationship that exists here. So when we're talking about, the heat at a constant pressure of the heat of that system is simply going to be the delta H for the system, right? So you can see the relationship here between the heat of surroundings and the heat of the system, right? If the surroundings is gaining heat, the system is losing heat. If the surroundings are losing heat, the system is gaining heat. So they're directly related to one another. So you can see when we're discussing the heat of the surroundings and the heat of the system and relating that to entropy, that they're going to be just obviously equal to the opposite of the enthalpy of the system. So the entropy of the surroundings is equal to minus the entropy of the system. And if you think about what that means, right? If we have our sealed container here again, right? And if we start increasing the heat of the system, so in this container here, right, we increase the heat here, what's going to happen, right? Heat is going to be transferred in infinitesimally small, amounts. We're going to be transferred to the surroundings, and the surroundings are going to increase in their entropy. Right? That's what's going on here, right? Because we have our system, and then we have the surroundings, and the surroundings, you can see this slight increase that occurs in the entropy of the surroundings. All right, and so if the entropy change in the universe is obviously composed of the system and the surroundings. So therefore, when we're talking about the universe in general, the entropy change in the universe is going to be equal to the entropy change of the system plus the entropy change of the surroundings. And, for a spontaneous process, this entropy change of the universe is going to be greater than 0, right? So if you have entropy, some type of process that occurs that's exothermic, right? An exothermic process which kind of occurs in a spontaneous fashion, we're going to have, the entropy change in the overall universe always be greater than 0. So if we talk about, the total entropy in relationship to spontaneity, so if we look at the top here, we have the entropy change of the universe is equal to entropy change of the system plus the surroundings, exactly what we said in the last slide. If we substitute for the entropy of the surroundings, right, because we just calculated that on the last, couple slides ago, so we're making this substitution down here, and we're plugging that into the equation, right? So if we plug that into the equation, we substitute in that we can see that the entropy of the universe, we can relate it directly back entirely to the system. So you can see now there's system components for both parts. So we don't have to measure the surroundings. We can just measure the entropy of the system and the enthalpy of the system, and we can relate that to the overall entropy change that's going to occur in the universe. If we, now it's going to be a little bit of mathematical manipulation. We're going to multiply both sides of the equation by minus t. And if we do that, then we see the minus t delta s of the universe is equal to minus t delta s of the system plus delta h of the system. We're going to rearrange this equation just to put it in this, rearranged order, where we just rearrange the delta t, minus t delta s, and the delta h of the system. So we place them on opposite sides. And that gives us this new equation, where we're going to now substitute in for minus t delta s of the universe, and we're going to call this term the Gibbs free energy. And we're going to give it a new term, so minus t delta s of the universe is equal to delta g. So this is the Gibbs free energy. This is going to, we'll talk about it in a second on the next slide, but this is the energy that's available in a system for a system to do work. And we get this new rearranged equation where delta G is equal to delta H minus T delta S when we're talking about constant temperature and pressure-based systems. So what this is going to tell us, we'll talk about here, is that when we have our free energy, right, the free energy is the ability of our system to do work, is going to be directly related to the enthalpy, which is related to the heat of the system, and the ability of the system to undergo disorder, right? So the more heat that's in a system, the more delta H, the larger the amount of free energy available for the system to do work. And from an entropy perspective, if you think about what's going on here, right? If we increase entropy, right, we are decreasing the amount of free energy that's going on in the system because we have a negative sign associated with that. We'll talk about this in more detail in the next slide. Right. And let's understand what Gibbs free energy means first. So the Gibbs free energy. So when we talk about delta G, if delta G is negative, the forward reaction is spontaneous. Right. So if we have a negative delta G, this forward reaction is spontaneous. I'll just read these off first, then we'll come back and discuss them a little further. If delta G is 0, the system is at equilibrium. If delta G is positive, the reaction is non-spontaneous, but spontaneous in the reverse direction. And when we're talking about what delta G stands for, right, we're going to say delta G is the free energy change, and that's the energy. I got a little green thing here. It's in front of my, can't read anything. All right, it's the portion of energy change of a spontaneous reaction that is free to do useful work. The remainder is released as heat. All right, so what we're talking about is the portion of the energy change of a spontaneous reaction that is free to do useful work. So let's take a look at the graph over here. All right, if we look at the graph, we have the reaction right here between N2 and H2 to give us ammonia. So what this is telling us, if our delta G is negative, then the forward reaction is going to be spontaneous, right? So if we look at the equation, write it up here, delta G equals delta H minus T delta S. And if we have our free energy is negative, that means a negative number is a good number. Remember when we talked about enthalpy back and last semester, any reaction that's giving off or has a negative delta H is going to be a good number, right? So negative delta H's are good. So when this is a negative number, this is a favorable reaction, right? So the same thing goes for delta G. If our delta G is a negative number, we have a favorable reaction. So what this Gibbs free energy is telling us is that if we increase entropy, right, this component of the reaction is also going to be a negative number, right? So the more disorder that occurs in a reaction, the more favorable the reaction is. And you can see there's two different components to the free energy of the reaction. If the free energy, we want it to be negative in order to have a favorable process. So if our enthalpy is very large, negative number, but our entropy, goes to a more ordered system as it does here, right? If you think about this, we're going from 1 plus 3 molecules, so a total of 4 gas molecules, down to 2. So from an entropy perspective, our entropy here is going to be negative, right? We're increasing order. So that's this whole right-hand side here, the minus T delta S is actually going to become a more positive number, which is going to decrease the delta H, which overall decreases the delta G, then the negativeness of the delta G. So from an entropy perspective, this reaction is unfavorable in the forward direction. So in order for delta G to be negative, our enthalpy of the reaction, the delta H has to be a large negative number in order for this forward reaction to be spontaneous, right? Now, if we think about the reaction in the reverse direction, right? In the reverse direction here, we're going from 2 ammonia molecules to 4. So now our entropy component, this is going to be positive, right? We're increasing entropy. So this is now going to be a positive, our positive number. This number is positive here, right? So when this number is positive, the minus T delta S becomes a larger negative number, which is going to be favorable. the delta H on this, in this case, is probably going to be going in the opposite direction, so be more positive. So in order for this reaction to be spontaneous, the spontaneity is occurring because we're increasing the entropy component of this reaction. So then delta G is going to be positive. So the overall delta G is probably going to be positive in this particular reaction. And because our entropy component probably won't be able to overcome this and overcome the positive enthalpy that occurs. So we end up having a reaction that's going to be favorable in the reverse direction, and it's favorable in the reverse direction because of our entropy component. And then when delta G is equal to 0, right at the center point, we basically have a reaction that's at equilibrium, right, where you've reached equilibrium and you no longer have this, you have the, delta H and minus T delta S are essentially canceling each other out. Let's go through a sample problem and see if we can understand what's going on here. So we have calculating free energy from delta H, T, and delta S. And you can see these are all the standard, right? We have delta S naught, right? There's the standard free enthalpies that we are able to look up in a table. It says calculate the standard free energy change for the formation of nitrogen oxide from N2 and O2 at 298 Kelvin. So we can see we have the reaction of N2 as a gas plus O2 as a gas gives us 2 NO molecules as a gas. And we're given that delta H is minus 180 kilojoules and delta S is 24.7 joules per Kelvin. So we want to know, is the reaction spontaneous under these conditions? So you would have been able to look this information up in standard tables. There are standard tables that you can look this information up in the back of the book, in the appendix. So to calculate delta G, we use equation 19.12, where delta G is equal to delta H minus T delta S. To determine whether the reaction is spontaneous under standard conditions, you're going to look at the sign of delta G. Solve it. There we go. Simply plug it in here, where delta G is going to be equal to 180 kilojoules minus 298 Kelvin times the 24.7 joules per Kelvin. And you need to recognize what's going on here, right? We need to convert from joules to kilojoules in order to match the units of the first part of the equation. So we convert over from joules to kilojoules. After we do conversion, you can see you end up 180 minus 7.4 kilojoules gives us a delta G, which is a positive 173.3 kilojoules. Since it's positive, this is not a spontaneous reaction under the standard conditions at 298 Kelvin, right? So we have this reaction is not going to be spontaneous. Means that if you mix nitrogen together with oxygen, this is not spontaneously going to produce nitrogen oxide. Is that a good thing or a bad thing? Anyone? Is it a good thing or a bad thing? If all the nitrogen and oxygen in our atmosphere reacted to form NO spontaneously, that's a good thing, right? This would be, because if this what happens, right, our atmosphere is made up of, what is it? Like, 60, 80% nitrogen and 20% oxygen, mostly, not including all the minor gases. We would consume all of our oxygen in the form of NO. We would have no oxygen to breathe, and we'd be in a lot of trouble, right? So it's a good thing this is not a spontaneous reaction, because we'd be in tons of trouble. And instead, all these nitrogen oxides, these are the types of gases that are given off by power plants and various other, any other type of combustion-based process. And these are a lot of the toxic gases that are found in the atmosphere. So if you think about it from a spontaneity perspective, it's more likely to go in the reverse direction over time, which is actually a good thing. Thank goodness our, we've been given, chemical processes that favor us producing oxygen, which is, could be kind of scary otherwise. All right, let's do a sample problem. Oops, too far. Let's go through a sample problem here. All right. So it says, using the standard molar entropies in Appendix C, calculate the standard entropy change delta S for the following reaction at 298 Kelvin. And I meant to pull up Appendix C beforehand, and I forgot. Let me grab Appendix C and get the numbers out, unless you have your textbooks handy. All right. So you'd obviously need to learn how to look up these numbers in Appendix C. Let's see. Appendix C, AL203. So if you would have looked up the AL203, is this the right problem? I'm not going to cover this yet. This actually doesn't cover this particular section. This is under the next section. You're all going to be kind of lost if I actually have you do this right now. This covers the next section. I must have either missed a problem or there wasn't a problem here. So we'll come back to this in a second. Just realized this is based on the next section that we're going to cover. My bad. We'll be back there in a second. No, it actually didn't cover the thing from the last class. It actually covers this equation right here. So I guess it is, we did cover it in the last class, but I wanted to cover this part a little more detail first and go through a sample problem. So I guess we did this, bring up this equation. So the standard free energy changes, let me see, I just want to cover this. Yeah, so it's going to be right after the next problem. So the standard free energy changes, so analogous to the standard enthalpies of formation are the standard free energy changes of formation. That's delta G naught sub F right here. And we have, we did this for entropy. In the last section, we discussed entropy. Well, we can do the exact thing now for free energy, right? So you can see this is very common, right? You can replace delta G with delta H, right? Naught, or delta S. Not, and you can simply look up these numbers in a table, and that allows you to very easily and quickly calculate the free energies or free enthalpies or free entropies or enthalpies of all of these different reactions. So you can just simply substitute it, and all of these are found in the table for certain types of reactions. Right, so this is the same thing. We're just basically going to sum up all of the delta G sub F's of all the products and subtract the sum of the delta G sub F's of the reactants. So products minus reactants. And obviously the N and the M are just the stoichiometry of the reaction. So if when we're thinking about standard free energies, remember this, what the standard state means. Right, the standard state of a solid is the pure solid. The standard state of a liquid is that pure liquid. Right, the standard state of a gas is actually 1 atmosphere of pressure of that gas. Standard state of a solution, right, is 1 molar concentration. Right, so this is something that we haven't talked too much about. When we talk about solutions, we're talking about 1 molar solutions being our standard state. And then for an element, the delta G sub F is equal to 0 for the element in its standard state. So, right, any element in its standard state is going to have a delta G equal to 0. If you think about, go through some sample problems, right? So I cut the data out already here for this problem, but we'll need it for the next one. It says calculating standard free energy change from the free energies of formation. You're going to use the data from Appendix C to calculate the standard free energy change for the reaction of P4 plus 6Cl2 going to 4PCl3 at 298 Kelvin. And then part B, we're going to ask what's the delta G for the reverse of the reaction. So if you were to look up your appendix, you would see in your appendix you would have these wouldn't be right next to one another. These would all be spaced out. I've taken, cut and paste them, put them here. But you would see a table that in Appendix C that gives you the delta H's, the delta G's, and the S naught, right? And you can see for pure substances, right? Chlorine is a pure substance, and chlorine exists as a gas in its in its standard state. So it's going to have a delta G equal to 0. Its delta H is also equal to 0. Now remember, with entropy is never going to be equal to 0 because unless we're at 0 Kelvin, right? Because we'd have to go down to 0 K in order to reach the standard state when we discussed entropy. So at 0 Kelvin, then the entropy will be equal to 0. So you'd have to go, because entropy is not standard at 298 K, whereas delta H sub F is 298 K is our standard. This is 298 K is our standard, right? So those are the standard temperatures. At standard temperatures, the delta H and delta G are 0 for pure substances. Phosphorus in the form of P4, in this case, that's not its standard state, obviously. So it's going to be, we have its delta G of 24, and then PCl3 is minus 269.6. So this is just a matter of now filling in and plugging into this equation here down below, right? So we're going to use the Gibbs free energy equation, right? We're going to multiply the molar quantities by the coefficients in the balanced equation and subtract the total for the reactants from that of the products, right? Products minus reactants. I already said that Cl2 is in its standard state, so delta G is 0 for this reaction. P4 is not in its standard state, so the delta G sub F is not 0 for this reactant. And then for the balanced equation in Appendix C, here's how we plug everything in, right? We have our products, the summation of our products, right? So we have the delta G of the PCl3 as a gas, and we have 4, right? There are 4 molecules, so we need to multiply that by 4. Then we're going to subtract the reactants. So if we distribute the minus sign, right, to both the reactants, we have the delta G sub F of P4, and since there's only one P4, right, there's only one P4 here, so we're only going to multiply by 1 mole. And then we're going to also subtract the delta G sub F of chlorine, which is multiplied by 6, right, because we have 6 here. And we simply plug in now the numbers. So 4 moles times the minus 269.6 kilojoules per mole. That's found in the table. Subtracted that by 1 mole times the 24.4 kilojoules per mole for P4 minus, this would have been beforehand minus 6 times 0, right? Minus 0 for the chlorine, right? 6 times 0 is just 0. And it gives you minus 1102.8 kilojoules for the delta G of this reaction. So delta G being negative tells us that this reaction is going to be move spontaneously in the forward direction, at least for under these conditions at 25 degrees Celsius, so 298 K. and partial pressures of 1 atmosphere. And so we're going to spontaneously form PCl3. Remember, however, the value of delta G tells us nothing about the rate at which the reaction occurs. Right? So if you mix P4 and Cl2 in a flask, it will eventually form PCl3. It could take a day, it could take 5 minutes, it could take 3 years, but the reaction would eventually be spontaneous. So that's all we know, is that the free energy is positive in the forward direction. Think about the reverse reaction. So if we reverse the roles of the reactants and products, all we're going to do is reverse the reaction changes and the sign of delta G in the equation. So, and that just as reversing the reaction change the sign of delta H to the opposite sign, all we're going to do for delta G is now for the reverse reaction, if we were to go through all the math, is just take the opposite sign. So delta G is now plus 1102.8 kilojoules. You can see it's pretty straightforward for figuring out free energy of a reaction. All right. So now let's go through a sample problem. There we go. So if you have your textbook handy, you can look up an Appendix C. An Appendix C would give you the delta G's for each of these, right? So the delta G for Al2. So I'm going to just draw it right below here. So this is minus 1576.5. And these are all going to be in, the units are all going to be in kilojoules per mole. The H2 is H2 is in its standard state, so this is going to be 0. Oh, they're looking for entropy. I'm sorry. You are correct. Good thing you're paying attention to the equation, the question. They're asking for entropy change. Huh. I guess you were right. They were talking about the entropy. So let me pull the entropy numbers up. This is per mole Kelvin. So now this is 51.00. Hydrogen is 130.58. It's a good thing I don't have to take this test, because I would fail. I would have got this wrong. I would have been calculating free energy instead of entropy. Aluminum is 28.32, and water is as a gas. So you should definitely look at this up, because you'd have to notice that this is in the gas and there are two numbers. There's one in the liquid, one in the gas here. So as a gas, this is going to be 188.83. All right, so take a few seconds and go through solve this. Yes, and that's because they're in the entropies in their standard state still have numeric values, because we're not at 0 Kelvin. At 0 Kelvin is the only time the entropy goes down to 0. So entropy is the one that never goes to zero, because the molecule is always going to be moving, right? As long as it's above 0 degrees Kelvin, 0 Kelvin. Whereas the enthalpy and the free energy are just all set at 298 Kelvin. Right. So hopefully when you get your number, pop it up in the chat. The units are up here in the left-hand corner. They're kilojoules per mole Kelvin. Let me do the math myself because I haven't actually worked through the problem yet. So you've all gone through it, hopefully correctly. So your delta S, right, seems to be delta S is just equal to 2 times 28, times the 28.32 plus 3 times 188.83 minus 1 times 51.00 minus 3 times 130.58, which equals 180.39. All right. Everybody can do simple math. Woohoo. Now, don't overcomplicate this on an exam. If you were asked this, this is one of the areas that people like to greatly overcomplicate. This is, what is this? First grade math, second grade math? When do you start learning multiplication? I'm proud of you too. All right. Very good. And then if we, from the unit perspective, just make sure you add, right? It's in kilojoules per mole Kelvin. All right, let's go back to the others, unless anybody has a question. No, Jason, most of the math.
Barbosa.
Yes.
So with S, isn't it joules, and then the delta H and delta G is kilojoules.
You might be right. I didn't look at the book correctly. Hold on. Did you look up the numbers in the book? I was quickly changing things, but it could be joules. I'd have to go back and look. Let me take a quick peek here. My textbook is off the floor here. You are correct. It is joules. So don't listen to me. I would have gotten unit points taken off. Good. It's a good thing I got students paying attention in class. So you're correct.
Hey, Dr. Barbosa.
Yeah.
This is right. I have a quick question. So you were subtracting, the entropy of the products minus the reactants, but you have like a subtraction sign, on the last one, minus 3 times 130.58. But should that be a plus sign, or are you subtracting both of them?
Yeah, so what I did was just, I took minus, if you do take a minus 1 times 51, 0 plus 3 times 130.58. And I just distributed the negative sign there and there, right? That's all I did.
Okay, makes sense.
And I distributed between both. Sorry, that was just a distribution step. So you could add those two first and then subtract it, or I just distributed a negative sign to both. Yes, you were correct as well. See, mole's not in the final units either. It's just Kelvin. You can multiply by moles. I'm in a hurry. There, mole. That's not working. I wanted to do something else. Let me see something. So there's no moles as the units in this particular example. So, right, there's moles that are canceled because these are each of these individual steps. So this is moles, right? This is moles. So all the moles are going to be canceled out of the equation. So you're correct, Annie. See, I really set you up. Make sure everybody's paying attention. I really do know what's going on. Don't worry about it. So make all the mistakes you could possibly make, and that way you know what to make, how to do it properly. So yeah, I'm just pretending to be the student that doesn't understand what's going on. I'm being very helpful right now. That's what I get for trying to go too quickly. There we go. Back to the presentation. What is going on? How did chapter 16 open up here? What's going on? Huh. I don't even know where chapter 16 came from. That was strange. All right. Back here. All right. Another sample problem. So we're going from one to the next. So in predicting and calculating the delta G of the free energy. So in section 5.7, if you think all the way back to chapter 5, we use Hess's law to calculate delta H for the combustion of propane gas at 298 Kelvin. So you can go all the way back and review that if you don't remember. Sensing negative energy from the universe. Yes. You're too. I won't go there. All right. So if you see the combustion reaction, right? So we have propane is C3H8 plus 5 oxygens gives us 3 carbon dioxide molecules plus 4 water molecules. And we would have calculated delta H overall for this reaction of minus 2,220 kilojoules. So without using data from Appendix C, predict whether delta G for this reaction is more negative or less negative than delta H. Right. So you need to predict whether or not delta G is more negative or less negative than delta H. So think about how we're going to work through that. And then part B asks, use the data from Appendix C to calculate delta G for the reaction at 298 Kelvin. Is your prediction from part A correct? So if we think about what's going on here, we have the free energy change, right, incorporates both the change in enthalpy and the change in entropy, right? We have delta G equals delta H, right? If we keep that equation up here, burn this equation into your brain. Right. So you can see if our delta H is a very large negative number, and they want you to then think about this in terms of enthalpy. Is this enthalpy component, entropy component, is that going to be more or less negative than delta H? So under standard conditions, you're going to determine, whether G is more negative or less negative than delta H. You need to determine the sign of the term of T delta S. What is the sign of the term T delta S? Because temperature is the absolute temperature. It's 298 Kelvin. It's always going to be positive, right? Temperature will never be negative because we're using Kelvin. We're using the Kelvin scale, and the Kelvin scale starts at 0 and then just goes up. So you're never going to have a negative temperature in any of these calculations. And you can predict the sign of delta S by looking at the reaction. Right, so if we look at the reaction, so the reactants, there are 6 molecules of gas, right? There's 1 C3H8 and 5 O2. And the products are 3 molecules of CO2 plus the 4 water gives us, but 4 water isn't going to be included because it's a liquid. So, and then they're going to be 3 gas molecules. So we're going from 6 gas molecules to 3 gas molecules. Number of molecules of gas has decreased significantly, right? We've gone from 3 to 6 to 3. By the general rules discussed in the section 19.3, we expect a decrease in the number of gas molecules to lead to a decrease in the entropy of the system, and the products have fewer possible microstates than the reactants, right? Because once we have this reaction, it's going to, you're going to have lots of gas molecules, but that water is just going to sit here as a liquid down at the bottom. So that's not going to be participating very much in the entropy of the reaction. And therefore, we'd expect delta S and therefore T delta S to be negative, right? So you're seeing going to a more ordered system. So you're going to have a negative, overall negative sign there. And because we are subtracting T delta S, which is a negative number, we project that delta G is less negative than delta H, right? I'm sorry. Right, so we're going to a more ordered system, right? So this component on the right-hand side of the equation, right? You're going to expect this to be, overall going to be a negative number. And that's going to overall going to, when you have this component be a negative number, right? Right, because in order to become more ordered, right, as we become more ordered, entropy is going to be negative. Everybody think about what's going on there, right? We're taking 6 gas molecules, right, and we're going to 3 gas molecules plus 4 liquids. And I'm not going to include the liquid. So you're going to have to, in order to go from a more disordered state to a more ordered state, you have a negative delta S, right? So a negative delta S is going to result in this overall side of the equation. When you have negative times a negative, this is going to be a positive number. So that's going to take away from the delta H component, the minus 22,220. So you're going to have a smaller delta G. Oops. Makes sense, hopefully. So you expect delta G to be a smaller negative number, so a less favorable reaction. All right, so if we then pull the numbers out of the for delta G out of the table in the appendix, and we plug it all in, right? So I'm not going to go through all the steps other than just show, right? We have 3 moles times the carbon dioxide plus 4 moles times the water as a liquid, plus 1 mole times the C3H8, and 5 moles times the O2. And we just pull the numbers out of the appendix and just do the math. And after we do all the math, we can see that we end up with a free energy of minus 2,108, right? So they just make a note, make sure you use the free energy of water as a liquid, not water as a gas, because both of them are in the table. So the phases of the, each of these are going to be very important, just like they are for enthalpy. So delta G is less negative than delta H, which, right, the original delta G, the delta H itself is minus 2,000. Okay, so delta H is equal to minus 2,220, right, kilojoules. So you can see that we're going to, we have a decrease in the enthalpy versus the enthalpy of the overall reaction. So our free energy is going to decrease. All right, let's see. I think I have a sample problem for this one too. Let's see. All right, very quick one. Let's try and make this quick. It says, which of these statements is true? So take the time, just write which one is true. Let's put the letter in the chat. So everybody seems to be coming together in agreement, right? We're talking about spontaneous reactions, right? The free energy is going to be negative, right? Delta G is going to be negative. It will be a spontaneous reaction that will occur. Right. You can look through the other ones. The other ones are all going to be incorrect. I'm not going to go through the explanations of each. Right. I just want to cover a couple more slides. All right. Free energy changes, right? So this is a nice table that kind of summarizes how signs of delta H and delta S affect a reaction spontaneity, right? So when we're talking about the delta G of a reaction, right? The delta G, right, we're talking about here is going to be affected by the enthalpy and the entropy, right? So if we look at the enthalpy of the reaction, if the enthalpy is a negative number and the entropy is a positive number, right? So this is favorably, the negative delta H is favorable from a reaction perspective. A positive delta S is favorable because the overall minus T delta S becomes negative. So overall, you're going to have a negative delta G. So this type of reaction is going to be spontaneous at all temperatures, right? The reaction of ozone to produce oxygen is an example of that reaction. If our enthalpy is unfavorable, a positive number, our entropy is unfavorable because it's a negative number, which ends up in an overall positive minus T delta S. We have a delta G equal to a positive number. So this reaction is not going to be spontaneous at all temperatures, right? Which makes sense that the reverse of the previous reaction, 3 oxygens are never going to go in the forward direction to make ozone, which is another good thing, right? It's a good thing that all of our oxygen molecules that we're breathing down here don't convert to ozone, because then we'd be breathing in ozone. If you have a favorable delta H, a negative number, an unfavorable entropy, a negative number, which results in an overall positive minus T delta S, you can end up with either a positive or a negative, depending on whether the delta H is larger or the delta S is larger, right? So at low temperatures, the delta H is going to be the dominant factor, and it's going to be a spontaneous reaction, right? Because delta H is going to be larger. At higher temperatures, the T delta S component takes over, right? When T delta S takes over, then it's going to be non-spontaneous, right? So think about what this means, right? If you take liquid water at a low temperature will freeze to become a solid, right? Makes sense, because you have the enthalpy component is taking over, right? Temperature is not affecting how fast the molecules are moving. You remove the temperature component, so the heat is the only effect on the reaction. And since you have a low amount of heat, because the temperature is low, you're going to freeze. Obviously, at high temperatures, you're never going to freeze liquid water. This makes sense, common sense, right? So if we look at the next possibility of positive delta H and a positive entropy, so of unfavorable enthalpy but a favorable entropy. So our T delta minus T delta S is going to be negative. They end up in the same situation, right? Where our positive or negative for delta G depends on the temperature. So now at a high temperature, we're going to have a spontaneous reaction, right? Where now at a high temperature, we're going to spontaneously melt solid water and form liquid water, right? So we're going to spontaneously go back and forth from a solid to liquid. Whereas at low temperatures, right? At low temperature, your solid water is never going to be formed into a liquid. Hopefully that makes sense. All right, so we'll pick up on the next slide here in the next class. And unless anybody has any quick questions, because I think I just ran right up against the end of the time. Otherwise, have a good day. I just wanted to check, see where we are in the slide deck. All right. Good day, everyone. Thanks, everyone.